Alright. Not yet. Okay. Are we working? Draw board. Ha! We're working. Okay. Looks like I got a few of you in here. Let me know if you can hear me. Technical issues. My one working tablet is a Windows tablet. Windows sometimes doesn't like to cooperate with me, but I think we're up and running now. Okay. Close that up. Move that up out of the way. Alright. Okay. Well, I know how I can tech. Windows tablet. Ah, there, I'm working. Okay. Check my own sound. Okay. Good, good. Alright. Let's get things underway. I think I can make that full screen. That works a little bit better. So, let's do some linear algebra. We'll do what we can under the circumstances. We need to finish off the chapter on determinants. We got to talk a little bit more about properties. We're going to look at some applications. We'll call her a day. And next week, we'll reconfigure next week. I don't know if this time is the best time. I gotta check, with you. I gotta check with my other class, figure out times at work. I gotta coordinate schedules with my wife because we're trading off between teaching and watching kids. We'll see how this works, but we're gonna try it for today. Okay, so here's some warm-up problems for you. I posted these up online, so hopefully you had a chance to look at them because with the live stream, I don't feel like I want to sit and give 10 minutes of dead air while you try a couple of determinants. We'll dive right in with these. So I'm gonna do that determinant A there, and if I'm looking at that, I see a couple of rows. There's a 0 there and there's a 0 there, and we know that if you're doing cofactor expansion, you want to pick a row or a column to expand along, right? The default definition says I should do, if we go across row 1, that I should do that 1, 1 entry times the 1, 1 cofactor, which is the determinant of that. And then I should do the 1, 2 entry times the 1, 2 cofactor, which is a minus sign plus the determinant of that. And then, 0 times the 1, 3 cofactor, but it's times 0, so we don't worry about it. But sometimes we like to do a row operation because it saves us a little bit of trouble. So if I'm deciding on a row operation, I think this is the easier bet, right? To do a row operation in the third column, I got to do fractions. There's an easier row operation here, right? I can do row 2 minus 2 row 1 into row 2. And if I do that, I need to change my pen size here. We'll worry about it later. When I do that row operation, I'm going to get a new matrix whose determinant is the same as the old matrix. So I can say that the determinant of A will equal the determinant that I get after that row operation. 1, 4, 0. And then, so I get 2 minus 2, 0. Minus 3 minus 8 is minus 11. 5 minus 0 is still 5. 0 minus 1 minus 2. Right? So now I want to do cofactor expansion down the first column, right? Because I'm going to get that 1 times, again, it's always plus 1 in that top corner. We always multiply by either plus 1 or minus 1, depending on which position we're in. In the 1, 1 position, it's plus 1. And then we multiply by this 2 by 2 determinant. Minus 11, 5, minus 1, minus 2. Right? And so that is going to be, so we do, as usual, we do this one, and we subtract that one. So minus 11 times minus 2, we get 22. 5 times minus 1 is minus 5, so we're subtracting minus 5. So we have 27 for the determinant. So it's not so bad, right? Now, you could, if some people, again, are playing around with this getting to triangular form, and you can do that if you want. But getting to triangular form is going to take a couple of row operations, because probably what you're going to have to do is you maybe want to get that minus 1 up there so you can use it to create a 0. So you'd have to swap those two rows. And then you'd have to take, minus 11 times that row, add it to the other one, make that other 0. You're at least 2 row operations away from triangular form. And, I mean, let's be honest, that 2 by 2 determinant is not that hard, right? So probably just get to that column of zeros and then we expand. And it would be a similar story for the 4 by 4, right? We don't want to do a 4 by 4 by cofactor expansion, right? Like, it would be very bad idea to expand along row 2, for example, because I'd have to calculate 4 cofactors, 4 3 by 3 determinants, right? I'd have to do minus 2, and that's in the 1, 2 position, so I multiply by a minus 1. So I do minus 2 times the minus 1, and then the determinant that I get when I delete that row and that column, right? So this 3 by 3 here. And then I do the 1, which is in the 2, 2 spot. Here's a plus sign. I delete that row, that column. We don't want to do that. That's too much work. So we notice that there is a column with a couple of zeros. There's a row with a couple of zeros. And so those are good choices, right? If we wanted to just expand without doing any row operations, I would probably just expand along row 4, right? That 4 is in the 4, 1 position, so the cofactor comes with a minus sign because I get plus, minus going down. So it would be 4 times minus 1 times that 3 by 3 determinant, and then that's minus plus minus, so it would be 1 times minus 1, and then this 3 by 3 here. But 1 3 by 3 is even better than 2 3 by 3s, so I think the easiest option is right here. To notice that, hey, if I add row 2 to row 3, I'm going to make another 0, right? Assume that these are usually a setup, right? There's usually a, there are other options we could do. There are other places we can make 0. There are other rows or columns we could expand along. There's often it's been set up so that there's a best choice. There's a simple thing you can do. So if I do that, if I take determinant of b and I do row 3 plus row 2 into row 3, then the determinant of b will be equal to the determinant of the matrix I get after that row operation. So row 1 didn't change, 3, 0, minus 2, 1. Row 2 didn't change. Row 3 does change. 0 plus minus 2, I get minus 2. Minus 1 plus 1, I get a 0. 2 plus 1 is 3. Minus 3 plus 3, I get another 0, which is convenient. Okay, and then 4, 0, 1, 0. Okay, so now I go and I say, okay, look, signs are plus, minus, plus, right? So that's a plus 1 in this position here. So what I should do is I should do cofactor expansion down that row, right? And I delete that row, or that column, sorry. I delete the column, I delete the row, and I write down the 3 by 3 that I get when I do that. So I get, well, it's 1 out front, because 1 is the coefficient. We write down that number. And then we delete the row and column. So we have 3, minus 2, 4, minus 2, 3, 1. And then, that's convenient, 1, 0, 0. Right? So you can probably guess that, tablet is wobbling, move some wires there. From here, if you're going to do cofactor expansion, you probably want to go along column 3, right? Because you already got 2 zeros there. And again, signs along that first row we always do it with reference to the determinant we're on, not the determinant we started with. Plus, minus, plus. Okay? So we're going to delete that column. We're going to delete that row. And we simply get that 1 from there times another 1, this one, times a 2 by 2. 2, 3, 4, 1. So we get minus 2, minus 12. We get minus 14. Okay. Got some questions. Okay, so let me get to the questions before we go on. So, first of all, why does the column have to be zeros? It doesn't. The only reason the reason I want zeros in my row or column is that, remember the rule for when you're doing if you're going to expand down a column, right? The determinant is going to be, so if I was going to go down, let's say column 2 in my 4x4, right? The determinant of B, if I did no row operations and I wanted to do column 2, I would do the so this is the 1, 2 entry, right? Row 1, column 2. B12 times C12, the 1, 2 cofactor. And then I do B22 times C22. And I do B23, 32, because we're going down the column. Right? So the row increases. We're now row 3, still column 2, C32, and then finally B42, C42, right? So technically there are 4 cofactors there that you have to compute. But if this number here, right, B1, so this one is a 0, this is a 1, this is a minus 1, and this is a 0, right? It's these numbers in this column, right? Well, I'm not going to bother calculating the C12 cofactor because I'm going to multiply it by 0, right? The cofactor is just a number. 0 times any number is 0. Similarly, I don't bother calculating the C42 cofactor because I'm going to multiply by 0, right? And I want to calculate as few cofactors as possible because each cofactor is a determinant, and determinants are kind of annoying, right? We want to minimize the amount of work that we do. Okay? So we can choose that column because we have 2 zeros. So now we only have to calculate 2 determinants, right? 2 3x3 determinants. But if I do this row operation, right? The reason I want to do this row operation is it gets rid of that number. It gets rid of the minus 1, right? Now I have a 0. So I have a new matrix, right? My new matrix is not the same as my old matrix, but I know that if I do this type of row operation, I'm not going to change the determinant. And so now, if I expand down that column, well, what happens is this entry here is also a 0. So I don't have to bother calculating the 3,2 cofactor because it's going to be multiplied by 0. That leaves me with only 1 cofactor, right? The fewer cofactors I have, the better. Now, as to Caitlin's question, what's with the plus and minus? Remember the definition of these cofactors, a Cij. By definition is minus 1 to the I plus j times the determinant of mij. This was the definition that we had. So mij, this here, that's a minor. Okay, so the minor mij, what that is that's the matrix that you get when you delete row I and column j, right? So the thing inside the determinant here, right? This bit here, this is the determinant of M. We were in row 2, column 2, right? This 1, it's row 2, column 2. So M22, I delete row 2, column 2, I get the smaller matrix, and then I take the determinant. Okay, and the determinant is not quite the cofactor. You have to put either this minus 1 or plus 1 out front. And so I plus j, I is the number of the row, j is the number of the column. and you just look at whether those two numbers add up to an even number or an odd number, right? Because this just means, you know, -1 times -1 times -1. If you have an even number of -1s, it's +1. If you have an odd number, it's -1. Okay, and so because, you know, if you're going across the row, right? If you're going across the row, the column number goes up by 1 each time. So 1 plus 1 here is even. 1 plus 2 is odd. 1 plus 3 is even. 1 plus 4 is odd. That's why it goes even, odd, and that's why it goes plus, minus, right? Because this one here, 1 plus 1 is even, you get a plus sign. 1 plus 2 is odd, minus sign. 1 plus 3, even, plus sign. 1 plus 4 is odd, minus sign. Similar thing here, right? Plus, minus, plus, because 3, the 3 is in the 1, 1 entry. 1 plus 1 is 2, is even, right? -1 times -1 gives you +1. That's where the minus signs are coming from. So yeah, go back and look. If you look at the examples we've done so far, you always got to make sure you got that sign factor, and you get these smaller determinants. So that's what you're doing when you're doing that cofactor expansion, right? So, for example, in the original matrix A, if I wanted to expand, let's say I wanted to go down, let's say I was doing row 2 for the matrix A. If I wanted to do that row, I wanted to calculate, because we have this Laplace expansion theorem. It says you can use whatever row or column you want. So if I went across row 2, okay, what it would look like is it would be 2 times -1 to the row 2 column 1, okay, times a determinant that I get when I delete row 2 column 1, which would be the 4, the 0, the -1, and the -2, right? And then I would go to -3, that's the second entry, -1 to the 2 plus 2. 2 plus 2 is even, so that's going to give me the plus sign, right? And then I write down the 2 by 2 that I get when I delete row 2 column 2, which is 1, 0, 0, and -2. And then I get the 5, -1 to the 1, row 2, so 2 plus 3, row 2 column 3, 2 plus 3, and then I delete row 2 and column 3, and I've got 1, 4, 0, -1, right? So then you kind of look and you say, okay, 2 plus 1 is odd, so I have 3 minus signs here. That's going to be a minus. 2 plus 2 is even, that's going to be plus. 2 plus 3 is odd, minus, okay? Oh, yeah, so just following up with, okay, yeah, the plus minus doesn't have to do with the numbers in the matrix, has to do with the position, right? So those signs, they come from the position and not the numerical value. So we take where the numbers come in, you know, in that cofactor expansion, right? The numbers are here, 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 right? There's the numbers. So the numbers come in, they multiply the cofactor, and the cofactor comes with this plus or a minus, and that plus or a minus is determined by the position of the entry. Okay, ready to move on? By the way, I know there's about a 10-15 second sort of latency here, so I'm watching my video on a screen so I can see your chat questions coming in, and the things I write appear up on the other screen about 10 seconds after I write them, so I'm trying to give you a second to ask a couple more questions before I move. I think I've delayed long enough that I can move on. So let's just recap, right? We talked about this already. I just want to remind you all that when you're doing row operations, right, you can, like, you know, a general matrix, doing the determinant with a cofactor expansion is messy, especially if it's a large matrix. If you don't have many zeros in your matrix, it's going to be a lot of work to compute the determinant. So you would like to simplify the determinant, and you can using row operations, right? So the idea here is you're always starting with A, and then you're going to do a row operation, and that gets you to the matrix B, right? And it says what happens. So if you swap two rows in the matrix, the determinant is going to change sign. If you start with A and you multiply a row by a scalar, maybe because you're trying to create a leading one, let's say, then the matrix gets multiplied by that same scalar. And the one that we really like is the last one, right? Because that third type of row operation is the type that creates zeros. The more zeros we have, the fewer cofactors we have to calculate, because cofactor multiplied by 0 is going to be 0. And also, this row operation makes zeros, and it doesn't change the determinant. So rather than trying to maybe get into triangular form, which can be a little bit touchy sometimes, you just make zeros. Make zeros, because the more zeros you have, the fewer determinants you actually have to compute. And just to give you an idea of why this works, right? If you think about elementary matrices, so if you think about taking, like the 3 by 3 identity. Okay, so that determinant of I is 1, right? 1 times 1 times 1. It's diagonal, so you can just multiply down the diagonal. If I do a row operation, like, let's say, sorry. My finger hit something that moved me. If I do a row operation like, maybe I switch row 2 with row 3, and I do that row operation, right? So then I'm going to get 0, 0, 1, 0, 1, 0. You can calculate what is the determinant of this matrix. The determinant of this matrix is going to be, maybe call that B. Determinant of that will be -1, right? One way to see that is if you did expand along, say, the first row, if you did a cofactor expansion along row 1, right, you're going to get 1 times this 2 by 2 here, and that's going to be 0 minus 1. So you see that you get -1 for the determinant. If you simply multiply, if you do like row 3 goes to 5 row 3, something like that, well, now you have 1, 0, 0, 0, 1, 0, 0, 0, 5. It's still diagonal. If you multiply down the diagonal, you get 1 times 1 times 5, right? So now the determinant is 5. And if you do something like row 1 minus 4 row 3 into row 1, well, one of the ways to understand why this third type of row operation doesn't change anything is that row operation puts a -4 up there in the corner, right? And notice that your matrix is now upper triangular, right? So if you do that type of row operation to a diagonal matrix, you get an upper triangular, and you still multiply down the diagonal, right, when you're doing the determinant of an upper triangular. So the determinant is still 1. So that's just, if you're wondering, like, why does this work, that's one way to look at it, okay? The main takeaway that I think I want most people to have for this is, if you're actually just computing a determinant, stick to this third type, right? Because it doesn't change the determinant, and it makes zeros. And the more zeros you have, the less you have to calculate. That's the philosophy you probably want to have here. On the other hand, we can always ask kind of questions to see whether you understand all 3 row operations by kind of, doing things like this. Okay. So I'm going to tell you that I started with a matrix A, right? So B is obtained from A using some row operations. So I start with A, whatever A happened to be, right? And now I'm going to do the first row operation, and that gets me to some other matrix. Let me call it maybe B1. It's not B yet. And then I'm going to do the second row operation, and I get to B2. And I do the third row operation, and I'm at some B3. And after the fourth row operation, I get to this new matrix B, right? And so now I can say that, what can I say? So that first row operation, I am multiplying by a quarter, right? So I can say this. I can say that the determinant of B1 is 1 over 4 determinant of A, okay? And I can say that the determinant of B1 is equal to the determinant of B2, because this is that third type of row operation, right? I'm adding a multiple of one row to another. B3 swaps 2 rows. So B3, determinant of B3 is equal to minus the determinant of B2, which is minus 1 over 4 times the determinant of A. And finally, that fourth type of row operation, again, it's the fourth row operation is adding a multiple of one row to another, which doesn't change the determinant. So the determinant of B is equal to the determinant of that B3. So in the end, what I get for the first question is this. Minus 1 over 4 times the determinant of A is equal to the determinant of B. And I'm told that the determinant of B is minus 7, right? That's given to me in the question. So I want the determinant of A, so I got to get rid of that minus 1 over 4. So I just multiply both sides by minus 4. And the determinant of A is 28. Okay. All right, I'm seeing some questions are still coming in from the last one. Let me get to that in a sec. The other way you can kind of think about this is if you want to think about a question like this, right? We could also think about this as, well, B is like E4, E3, E2, E1, A, where those E's are elementary matrices. And the determinants of each one, the determinant of E1 is 1, the determinant of E3 is minus 1, the determinant of E2 is 1, the determinant of E1 is a quarter, and then I have determinant of A. That's another way to think about what we just did, right? So that minus 1 quarter, get rid of that, and I've solved for determinant of A in terms of determinant of B. All right. Let me get to your questions as they're coming in here, and then we'll do the next one. Okay. Right. So question from Chris: if you pick row 1 as the cofactor, does that mean column 1 is also picked? Right. So that would be coming back probably here, right? So yeah, you decide. It's not elementary because you're actually this is actually 2 row operations in one. What you would do here is you're first actually changing row I into minus row I, and then you're adding k times row j to it. So the adding k row j doesn't change anything, but swapping the signs does. That actually changes the sign on the determinant. So yeah, I think I mentioned this last week. You do have to be really careful about this. Row 1 plus row 2 is okay. So the one that Chris gave in the chat is if I'm doing row 1 plus row 2 into row 2, okay? That's fine, okay? If I did minus row 1 plus row 2 into row 2, that's fine, because I'm leaving row 2 alone and I'm adding a multiple of row 1 to row 2, right? I'm doing minus 1 times row 1 added to row 2. But if I did row 1 minus row 2 into row 2, that's wrong. That won't be elementary, and it's going to change the sign on your determinant, and you're going to be off by a minus sign at the end, and you won't wonder why. The only way you get the right answer if you're doing that is you do that kind of thing twice, and you get 2 minus signs that cancel out in the end. Otherwise that's going to get you into trouble. Good. And then, okay, it looks like the last one was just a response to Chris's question. Okay, I'm going to come back to the second question that I had here. Suppose you've got a 4x4 matrix, and you know that the determinant is minus 3. What can you say about the determinant of 2 times A? So there is a property, and it's going to be coming up right away, and it's derived in the textbook. But if you think about how do you get from A, going from A to 2A, think about that in terms of row operations. Well, you'd actually have to do 2 row 1 to row 1, and you do 2 row 2 to row 2, and you do 2 row 3 to row 3, and you do 2 row 4 to row 4, right? When you multiply a matrix by a scalar, every entry in the matrix gets multiplied by that scalar. So every row is getting multiplied by the same scalar. And every time you multiply a row by a scalar, the determinant gets multiplied by that scalar, right? And so that means that basically we take A, so we'd have the determinant of A, right? And then we do times 2, times 2, times 2, times 2, right? We have to double for each of those row operations. So that means that the determinant of 2a would be 2 to the 4th power. Sorry, that was not a good 4. 2 to the 4th power times the determinant of a, which is minus 3. So 16 times minus 3, or negative 48. Although, honestly, if you left your answer like that, that's perfectly fine. I don't care if you do the arithmetic. In general, the rule for scalar multiples is you get that scalar raised to the nth power for an n by n matrix. So for a 4 by 4, we should raise to the 4th power. Okay, so those are some examples playing around with kind of effective row operations. Next up, we want to look at properties. Okay. I'll give people a chance to ask a question. Oh, while I'm waiting, water. All right, let's press on. I see that I'm half an hour into my stream already. I don't see any questions coming up, but I might be underestimating the latency. Okay, here are some properties of determinants. This was my very last slide on a week ago that we didn't quite get to. Determinant has some nice properties. It works well with respect to multiplication, right? So some people, if you like to use the vertical bars for determinant, this is saying that the determinant of AB is determinant of A times determinant of B. It makes sense that taking the transpose doesn't do anything because you can expand along a row or a column, right? So expanding along a row of the transpose is like expanding along a column of the original matrix. And this last one here, that's the one that we just talked about, right? What happens if you do scalar multiplication? Notice that there is no relationship between determinant of A, determinant of B, and determinant of A plus B. And so in general, we kind of, I would say we just say this, we can't say, I'll say anything about determinant of A plus B. There is no rule that we can use for determinant of A plus B. Okay, so there's no addition rule. The only way to calculate the determinant of a plus B is to actually plug in the matrices and add them together and then take the determinant. There's no nice rule like there is for products. A big one here is this last one. And this is one of the reasons why people care about determinants. The determinant gives you a very easy test for invertibility, right? And so the way to understand this, I mean, in one direction at least, if your matrix is invertible, there's an easy way to see where this formula comes from. So if A is invertible, we know that by definition that means that A times A inverse is the identity, right? There we have this other matrix, A inverse, so that the product is the identity. Oh, and for Peter's question, yeah, all this stuff gets saved automatically to YouTube, including the chat. So we'll, yeah, you'll be able to get it later. You can even, I think you can even pause it if you want. You can, if you don't like something, you can pause. You can come back to the live, or you can just watch on a delay. You can pause the live feed if you want to. So A times the inverse is equal to identity. So you can take the determinant of both sides. So determinant of A times A inverse is equal to the determinant of the identity. Okay. Now we can use that product property. So the determinant of A times the determinant of the inverse. Well, the determinant of the identity is just 1, right? Because we just multiply all the 1's on the diagonal, and 1 times 1 times 1 times 1 is still 1. Okay? And, well, now you can see it. So if A has an inverse, the determinant can't be 0, because if this was 0, well, there's no way I can multiply by another number and get 1. So determinant of A has to be non-zero, and since it's not 0, you can divide by it. And the determinant of A inverse is 1 over the determinant of A, right? So for some people, this is a nice property because you get frustrated that you're not allowed to just divide by a matrix, right? 1 over A makes no sense. We can only talk about multiplying by an inverse. We can't talk about dividing by A. But once you take determinants of everything, right? Once you take determinants, now you have numbers. And it does make sense to divide by a number. So you do have this relationship, and you can kind of see how, okay, yeah, this idea of inverse is kind of related to the one that we saw before for numbers. So you can do that. The other direction, it's a little bit trickier to show that if the determinant is non-zero, that guarantees your matrix has an inverse. There's a bit of a discussion on that in the textbook if you want to see it. It more or less boils down to playing with row operations and thinking about, well, what does it mean to say the determinant is not zero? Or maybe another way to say it is the other way to prove that if the determinant is not zero, then the matrix has to be invertible. That turns out to be logically equivalent to saying that if the matrix is not invertible, then the determinant is zero. And that one's actually not that hard to show because if your matrix is not invertible, reduced row echelon form is going to have a row of zeros. Expanding along a row of zeros is going to give you 0 for the determinant, and you can sort of argue along those ways. All right. And answering Julia, the n in the third property, that is the number of rows. So the n up here matches the n here, right? So for an n by n matrix, n is the number of rows. Oh, we're losing Julie. Has a test. Oh, I bet it's the chem midterm. Yeah, that's my fault that they can run it. I gave them crowd mark. All right, ready to move on? Let's move on. Let's do some examples. We can always jump back. If I see a question, I'll jump back if I have to. So here's a typical kind of basic computational problem. So you're told that the determinant of A is 3, you're told the determinant of B is -2, and you're asked for these values. So the wrong thing to do here is to try and reverse engineer, and actually you don't want to bother coming up with a matrix A that has a determinant of 3 and a matrix B that has we don't actually need to know what the matrices were. All we need is the determinants, because for this, we can say, well, determinant of A squared times B cubed. Well, that's what? That's the determinant of A times B times B times B. And you can use that product property, for products of 3 or more matrices as well. So now you have determinant of A, determinant of A, determinant of B, determinant of B, determinant of B, or if you like, determinant A squared, determinant of B cubed, right? We can just do that. So then we just plug in the numbers. 3 squared times -2 cubed. Leave your answer like that if you want. Otherwise, that's what? 9 times -8, so it's minus 72. Okay. All right. So let's go on to the next one. Determinant of B inverse times A times B. How do we tackle that? Well, let's put it down here. So we get the determinant of, so using that product property, we get this. Determinant of A, determinant of B. Okay. But then we also know the determinant of B inverse is 1 over determinant of B. Right? And so what's interesting here is that we actually get cancellation. We just get the determinant of A. And determinant of A is, well, 3. One thing I want to emphasize before we move on. The original matrix is not equal to A. Right? B inverse and B, these here, we can't cancel them because the A is in between, right? You can only cancel a matrix with its inverse if they're adjacent. If there's something in between, they don't cancel. Okay, but once you take determinants, you're dealing with numbers, right? And we can change the order of multiplication for numbers, so now we are allowed to cancel. This is going to be important once we move to eigenvalues and eigenvectors. There's a name for this property where you take a matrix and you multiply on either side by some other matrix and its inverse. We would say that this new matrix here, B inverse times A times B, we say it's similar to the matrix A. And essentially what this shows is that if you have two matrices which are similar, they have the same determinant. We'll show later on that they also have the same eigenvalues. All right, and then finally for that last one, if I'm doing the determinant of 2a times b inverse, well, I can write that as determinant of 2a times determinant of b inverse, and I didn't give. I think we're ready to talk about applications. How are we doing? We're doing okay on time. So there are two applications. We're going to go through them just so we can say we've done them. I will caution people that these, although we call them applications, they're actually more theoretically interesting than they are practically interesting. We'll get into that. I did have more examples. Okay, let's do these quickly. So here we have some properties satisfied by a matrix. We want to say, yeah, let's do this. I don't want to skip it. They're good. So if I know that a squared is equal to a, right? So that's saying that a times a is a. I can take determinant of both sides. Determinant of a times determinant of a is equal to the determinant of a. Okay. Or in other words, I could write it like this. Determinant of a squared minus determinant of a is 0. Or I could write that as determinant of a times determinant of a minus 1. If you're wondering why I'm gathering and factoring, it's because a lot of people, I bet a lot of you were tempted to do this, right? You're like, hey, look, it's on both sides, let's cancel it, right? Right. Similarly, like up here, you're probably like, oh, a squared is equal to a, so that means a is the identity, right? No, it doesn't actually have to be the identity. If it's invertible, yes, but maybe a is not invertible. There might be non-invertible matrices that satisfy that equation. A squared is equal to a, and now we can see why, right? Yeah, we could have determinant of a equal to 1, but we could also have determinant of a equal to 0, right? There are actually two possibilities there. So 0 or 1. Okay. A to the 4 equal to I. Well, that comes down to the determinant of a to the 4 is equal to the determinant of I. Determinant of I is 1. And so, if you think about trying to solve like x to the 4 is equal to 1, there are two values that work. X could be plus 1 or minus 1. So determinant there would have to be plus or minus 1. Okay. For that last one, determinant of PA would be equal to the determinant of P. Use the product property on the left. Determinant of P is equal to the determinant of A, or determinant P times determinant A is equal to determinant P, right? P is invertible. That means that the determinant of P is not 0. Since it's not 0, I can actually divide by it. And this time, I can actually say the determinant of A has to be equal to 1. Okay. Let's check. Don't see any new questions. There we go. I'm watching myself right on the screen. Very good. Let's move on. Applications. I don't have my section heading. All right. We're on now to, this is under a heading. I get section headings in the HTML versions, but the HTML is hard to annotate, so I did the PDF as well. So this is under kind of a formula for determinants and the inverse of a matrix. Okay. So starting point is this so-called matrix of cofactors. So again, here's that formula that I put up at the beginning, right? The cofactor is a number. And the way you get that number from a matrix is you delete a row and a column, right? So you get a minor. So for a given I and j, you delete row I, column j. You take the determinant, and then you multiply by this sign factor. So just to give you an example, here's a 3 by 3. Okay, so if and let's just do this longhand just so we get the hang of it, right? So C11, right, is minus 1 to the 1 plus 1 times the determinant that I get when I delete row 1, column 1. All right, so I'm hoping that this will also help nail down this idea of cofactor. So if we delete that row and that column, I'm left with 4 minus 2 minus 1, 0. Okay? So 1 plus 1 is even. So this is just going to be plus 1. Right? 4 times 0, I get minus 2. Right? So this here, that's a plus. Right? That's plus. That's 0. That's 2. So 0 minus 2 gives me the minus 2. Okay? C1, 2. So 1, 2, that's row 1, column 2. So if I delete row 1, column 2, I've got this and I've got this. So 0, 1, minus 2, 0. And this time, so this was a plus. This is actually a minus because 1 plus 2 is odd. 0, that's minus 2, but it's minus minus 2 because we subtract that, right? So this determinant is 2. There's a minus sign out front. Minus 2 again. C1, 3. Minus 1. And by the way, once you get the hang of the signs, you don't bother writing this minus 1 out front. You just put a plus or a minus. Yeah. Row 1, column 3. Remove those. If I remove those, I've got this determinant here. 0, 1, 4, minus 1. And again, this is plus. 0 minus 4. I get minus 4. Okay, on to row 2. Now I'm row 2, column 1. Okay, this time let me actually put those signs in. So 2 plus 1, right? Row 2, column 1, 2 plus 1 is odd. So I get minus, plus, minus, right? And down here it's going to be plus, minus, plus. And again, it's all about position. The numbers don't matter, it's all about the position. Okay, so I get a minus sign out front. And by the way, notice that these are just the cofactors, not the numbers that they get multiplied by, just the cofactors. Okay, so if I delete row 2, column 1, I'm left with these numbers and these numbers. Minus 1, 3, minus 1, 0. So that's going to be minus 3. Okay, let's come up here. C2, 2. It's going to be plus sign out front. I get the numbers in the corners. When I delete row 2, right, I'm going to delete row 2, column 2. I get the 4 corners, 2, 3, 1, 0. That's minus 3. 2, 3. Minus sign out front. I'm going to delete now row 2, column 3. Leaves me with those entries. 2, minus 1, 1, minus 1. So that is minus 2 plus 1. So I get minus 1, but there's a minus sign out front. So I get 1. Okay? All right, on to row 3. Let me do row 3 a little bit faster because this gets kind of boring, right? 3, 1. Plus sign. We want to delete now row 3, column 1. That gives me these. Minus 1, 3, 4, minus 2. Okay, so 2 minus 12, I get minus 10. 3, 2, minus sign out front. 2, 0, 3, minus 2. That's these and these because we're deleting that stuff. And so I get minus 4, minus sign out front, 4. One more, plus sign. and deleting row 3, column 3 gives me that. 2 minus 1, 0, 4. I get 8. So this cofactor matrix, I just replace each entry by the corresponding cofactor. So minus 2, minus 2, minus 4, minus 3, minus 3, 1, minus 10, 4, and 8. All right, we'll explain why we need this in a minute, but now we have it. Okay, so this cofactor matrix is going to be useful. We're going to see how to use it to calculate inverses in a minute, but I hope that even for a 3 by 3, you can see that this is kind of a pain, right? You got to calculate all 9 of those 2 by 2 determinants. And if we were, now imagine I wanted the matrix of cofactors for a 4 by 4. For a 4 by 4 matrix, I have to calculate 16 cofactors, and each of those cofactors involves a 3 by 3 determinant, right? So I will promise to never force you to do a matrix of cofactors for a 4 by 4, because that's ridiculous, right? 5 by 5, you got to calculate 25 4 by 4 determinants. No, forget about it. Nobody wants to do that. So we'll see. We have a nice formula. It's interesting, but it's not going to be super practical. Okay, so what do we use it for? Well, we can take the transpose of this thing, and we get something called the adjugate. So the adjugate matrix is you just take all the cofactors, and then you transpose that thing, okay? So if I'll try to remember what I had here. Minus 2, minus 2, minus 4, minus 3, 1. Let me see, did I get that right? I think I did. Okay, so this was our cofactor matrix. I transpose, and I get minus 2, minus 2, minus 4, minus 2, minus 3, 1, minus 10, 4, 8. So this would be the adjugate of A, where A was, let me remind myself on A, 2 minus 1, 3, 0, 4, minus 2, 1, minus 1, 0. Did I get that right? Yeah. Okay. Now, the reason, you can kind of play around and you see what happens here is if you take, say, the first row of A and the first column of the adjugate, okay? Well, so you would do, what would you do? You do 2 times minus 2, minus 1 times minus 2, 3 times 4. But that's doing 2, right? These entries came from here. So you're actually doing cofactor expansion. 2 times minus 2, minus 1 times minus 2, 3 times minus 4. That's the determinant, right? That's determinant computed using cofactor expansion along row 1. And so if I did A times the adjugate, okay, if I do that, I'm going to get minus 4 plus 2 minus 12. So I get 12, I get minus 14, okay? And now you can check that if you do that row times the other 2 columns, you get minus 4 if I did it right, and it's possible I did it wrong. Let me make sure I just got 2 minus 1, 3, and minus 3, 1. I may also have a calculation error. It's easy to make calculation errors on these. I should get 0 when I go down the next one. Minus 4 plus 3 plus 3. I'm not getting 0. So something is wrong. Minus 20. It works here. So something in that middle is incorrect. Let me go back and see if I can find my mistake. So the middle rows I did something wrong. Minus 1, 3, minus 1, 0. 0, 3, minus 3. 2, 3, 1, 0. Should be minus 3, 2, 3. Minus 2, plus 1. Minus 1. Seems okay. Alright. I've done something wrong. And I can't find it, but you know what? We're running out on our time. Minus 2 in the second row should be a minus 3. Minus 2 in the second row. Here. Wait. Oh, of the original matrix. 2 and 3. No. Cofactor from the last slide is wrong. Okay. 2 minus 2 minus 2 minus 4. Minus 2 minus 3. There it is. I got it. Yep. Thank you. That's a 3. Okay. So that's a 3. And that does give me a 0 now. Good. All right. Thanks, everyone. Okay. And then if we do, so now if we do row 2 times, so going, doing the multiplication, this row times that row. So I get 0 minus 8 plus 8, right? 0. Second row of A times the second column of the adjugate. That's like doing cofactor expansion along row 2 of A, right? It's doing A21 times C21, right? A21, C21, A22, C22, A23, C23. That's determinant expanding along the middle row. And you can check that you again get minus 14. And I'll trust that the rest is right. Okay, so this is actually minus 14 times the identity. And this minus 14 here is actually the determinant of A. Okay, so what this boils down to, right, is that you can divide by determinant over here and you get something that looks like this. A times 1 over determinant of A times the adjugate is equal to the identity, right? But if we have A times something equal to the identity, that something must be an inverse, right? So the inverse of A is 1 over the determinant of A times this adjugate matrix. So this gives you another method for computing the inverse of a matrix. But like I said, if it's a large matrix, it's a terrible method. Row operations are definitely more efficient, right? Row operations will always be more efficient than using this formula. Determinants take a lot of work. Some people really like this formula, but trust me, it's more work than row operations. For 3 by 3, maybe you break even. It's only slightly more work for 3 by 3. But as things get bigger, it's way more work, right? You would be a bad computer programmer if you programmed your computer to compute inverses this way. Okay. All right. Since I'm coming up, I said I would do this for an hour. I mean, we normally do 75-minute classes. You can always drop out if you need to go. I'm gonna leave this one here as an exercise. I want you to try it and post your answers up on the forum, right? You got the Piazza forum there. Give it a try. Put your answers up. You can compare answers. We'll see if people get the same answer or not. If a bunch of you get the same answer, we can be pretty confident that you got it. Now, notice this next one. Here's a place where you actually want to use this formula, right? You want to use this formula when you have variables in your matrix, because doing row operations when there are variables gets tricky. People struggle with row operations when there's variables involved. Okay, now you probably want to use the adjugate formula. It's going to be a little bit easier. So if I want to calculate the inverse for this matrix using the adjugate formula, well, again, the first thing I got to do is I got to get that matrix of cofactors. Okay, So I'm going to do this maybe a little bit fast because I want to get things done and get us out of here. The 1, 1 cofactor is going to be just minus 3x. Okay. Okay. And then the 1, 2 cofactor, I'm going to have minus 2x. And then I'm going to have, for the 1, 3 cofactor, I'm going to have x squared. Okay. Then I'm going to have 0. I'm going to have 3 minus x squared. Oh, I got to be careful. I'm missing a minus sign, aren't I? Haha. Let's remember our signs. Okay. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So that 2x, that should be a plus, right? Because we get minus 2x, but the extra minus sign makes that into a plus. Okay. All right. Finally, on to the 2, 3. I've got that pair of zeros there is going to give me another 0. Down to the last row. Okay, so the cofactor for the row 3 column 1, I've got actually x squared. Okay, then I've got actually minus 2. So that minus 2 comes from doing 1 times 2 and then x times 0, right? So just 2, but it's in a spot with a minus sign, so I get a minus 2. And then finally I've got minus x. Okay, so I can get that. I can also get the determinant of a. And let's just do cofactor expansion along. Well, actually, let's do cofactor expansion down the middle. So we only have to do one of them. Okay, so we get minus x times the determinant we get when we delete that column and the middle row. 1 x 3, right? Which is, of course, that middle cofactor. So we get minus x times 3 minus x squared. So we can write that as x cubed minus 3x, right? And so then the inverse is going to be 1 over x cubed minus 3x times, we got to take the transpose, right? Transpose of the cofactor matrix. So minus 3x, 2x, x squared, 0, 3 minus x squared, 0, x squared, minus 2, minus x, right? And I guess we should also kind of point out that, well, this makes sense as long as x is not equal to 0 or plus or minus square root of 3, right? Because those are going to be the values of x where the determinant is 0, and so the matrix is not invertible for those values where the determinant is 0. So this is somewhere where that adjugate formula might actually be useful, right? Otherwise, it's kind of a theoretical thing. It tells us that another way of kind of computing the inverse, but yeah. I know for some people, throwing all the x's in there probably makes it look a little bit intimidating. You'd rather do it with the numbers, and that's fair. Most of the ones that you see are going to be with the numbers. But if you're wondering, like, why does somebody bother with this formula if it's actually more work? Well, here's a situation where this formula is probably easier to deploy than doing row operations. Okay. So the last thing I'll mention, and then we're going to wrap this up. I'm just going to mention this to you. Cramer's rule. So Cramer's rule is an interest. It's a curiosity. It's a cool thing, but again, it's not something that you really want to use in practice. Where Cramer's rule comes from is you start with a system of equations, right? And we know we can write our system in matrix form. A times x is equal to b, right? B is just that column, the column of constants on the right-hand side of each equation. And if A is invertible, well, then we can solve for x. We've seen this story before as well, right? But then you can take that formula that we just found for the inverse and plug it in, and you get something that looks like this. So you get 1 over the determinant times this product here. And you can work out that the entries in that product are basically what you get if you take the original matrix A and you replace one of the columns by the constants on the right-hand side. And so you get this formula. So one thing that's kind of cool about it is you can solve for individual variables. You don't necessarily, if you just wanted to know the value of y in a system involving x, y, and z, you could use this formula to get it, right? But again, computing two 3x3 determinants is probably about as much work as solving the system. And you still have two more variables that you have to solve for. So the only thing that's interesting about this is Cramer's rule, and actually determinants themselves, they actually predate matrices, surprisingly enough. And so Cramer's rule was a way of solving systems that was around before people discovered row operations and matrices. This is a much older way of solving systems. In fact, it's named after this guy Cramer. I don't really know his story, but you can find examples of this method in texts going all the way back to like ancient China. It's been around for a long time. Okay, so here I give you a scary looking example to, you know, again, somewhere where you would use Cramer's rule, 2x2 system. You would solve a 2x2 system using row operations. It's faster. But here your matrix A looks like this: cos theta minus sine theta, cos theta. And now you do need one trig identity here. The determinant is cos squared theta plus sine squared theta, which is 1. Convenient. Now the A1 in the notation for Cramer's rule means take column 1 in A and replace it by the constants on the right-hand side. So instead of cos theta sine theta, we put 4 and we put W. Okay, so the determinant of A1 is 4 cos theta minus W sine theta. And Cramer's rule says that's going to be x. A2, you know, so I mean, just jumping back. Why is it x? Well, it should be that determinant divided by determinant of A, but determinant of A is 1. Dividing by 1 doesn't do anything. Okay, and then for the other one, A2, we replace the second column of A by the constants. So cos theta, sine theta, they stay put, and we put the 4 and the W over here, and we get W cos theta minus 4 sine theta, and that's why. Okay, so there's Cramer's rule. It's weird, but it works. I don't recommend using it solving systems with numerical coefficients because row operations are more efficient. They'll get you the answer faster with less chance of mistakes. But it's there. It's an alternative method. You have it as an option. That's all I got for you today. Before I go, I'll talk for a minute in case people want to throw last-minute questions up there. I don't have a schedule for you yet. I just want to mention that we haven't quite scheduled things. I'm going to try to go for the last 2 weeks on a regular schedule. We'll have a set time for the lecture. I'll have set times that I promise to be up on Piazza answering questions. I might even have a set time where we use Zoom for a live office hour where you can phone in or like video call in. We're going to do all those things. I'll probably put another survey up on Moodle just to figure out, you know, which times are going to work for the majority of people. Oh, somebody found a mistake. It should be plus. Yes, minus. Thank you. Good. Yeah, so I'll try to get that figured out on the weekend. I got to coordinate. I got my other class I got to fit in. I got my wife's teaching schedule that we got to fit in because we got the kids at home. Once we get everything all sort of slotted in, I will post a schedule up on Moodle. We'll get that figured out this weekend, and we'll do more of this next week. We'll stick to sort of Tuesday, Thursday for the classes like we've been doing, and we'll see how it goes. I'll look at my analytics. I'll see. There's 40 of you watching now, so I guess that was worthwhile. That's about a quarter of the class, a little less than a quarter of the class. Hopefully some of you will watch later. We'll see how this goes. All right. Well, that's fun. Sorry we can't be meeting in person, but at least we were able to do a little bit of math. I'm going to end this stream, and if you do have more questions, please hit me on that forum. The one thing you can all do to help me out as far as kind of keeping on top of stuff here is put all your homework questions up on the forum. It's going to be easier for me to answer that there. And yeah, we'll see what we can do. All right. Thanks for tuning in, everyone.